next step at balancing more complex reactions using the half reaction method. Knowing that when Leo says grr, we really start to think of reactions in terms of two halves. If one of the half reaction loses electrons, it ends up on the product side. The other has to gain electrons. It ends up on the reactant side. On our notepad page, we see that we're to fill in the word produces and requires. If one produces electrons, that really is the Leo half reaction. You're going to see those as products. So literally on the right-hand side of our arrow, we're going to start noticing that we're making electrons. Now electrons appear in half reactions, but they do not appear once we combine them back to create a full balanced equation. And over here, if this is the grr half reaction, where reduction means that we're requiring electrons, keep in mind that electrons are going to be written on the reactant side of our half reaction method. And the whole game as we learn how to balance equations is that Leo has to equal grr. Ultimately, when we look at an equation, other than just eyeballing it with coefficients, and we're pretty good at that, sometimes reactions are a little more complex and we can't just spot it by looking back and forth at reactants and products. We have to follow a series of steps that help us balance equations by splitting them in half. We're going to look at a complex reaction and begin to split it into two parts, balance each half of them, and then put them back together. So ultimately, we begin by practicing writing the half reactions. So in a notepad page, we see just a practice in writing half reactions for the following. I see where I have a sodium atom, and I know that it starts neutral, reacting with a chlorine molecule, again uncombined state, so we know its oxidation state is 0. Over here, we're forming ions of those two elements, a sodium with the +1 and a chloride with a -1. Now I bet with this simple reaction, what we're able to do is just to eyeball it back and forth and put in coefficients. But the practice here with the simple one is to recognize what are called half reactions. What I notice is sodium going to a sodium ion. To write that as a half reaction, I write sodium atom as no charge, forming a sodium ion with a +1 charge. Now this is the beginning of a half reaction. What I notice is it's not balanced based on charge alone. That so far I have a +1 on one side and a neutral charge on the other. That's just recognition that it's not a balanced equation. What I also notice is chlorine. It started as a 0 and went to a -1. So to begin with, I'll just separate those two half reactions. I'll show chlorine molecule as Cl2, forming the chloride ion as a -1. So in our very first steps of recognizing how to split them apart, we take the balanced or the unbalanced equation we were given and just recognize that one is changing charge from 0 to +1, the other is changing charge from a 0 to a -1. When I think about up here, sodium going to sodium ion, the number of sodiums are the same. I have a number of Na is 1, and over here I have a 1. But to make them electrically balanced, if this is a 0 and it's going to a +1, when I add electrons, remember that makes it become more negative. To bring this positive side down, I can see that this lost 1 electron. And losing an electron is going to form what's called an oxidation half reaction. The loss of an electron is oxidation. So far, we've shown sodium atom losing 1 electron, forming its +1 ion. There's the Leo. In the second half reaction, Cl2 forming chloride, what I recognize is that I can easily place a coefficient, 2 chloride ions, to just simply balance the number of those atoms. If Cl2 needs to be balanced, I have to place a coefficient in front of the chloride. Now over on this side, the net charge is -2, 2 units of a -1 ion. The net charge over here is a -2. Now remember, to balance half reactions, they just have to be the same charge on both sides. Not that they both have to be 0, they just have to be both the same. And what I'm allowed to add, is this whole thing is about redox and its electron transfer, I'm adding negative charges. So if this side is a -2, to make them both the same charge, I'm going to add 2 electrons to the left-hand side. 2 electrons on this side make both the same net charge of a -2. And I could see that if the first half reaction lost electrons, the second half reaction has to gain, because wherever there's a Leo, there's got to be a Gur. The game now says Leo, the loss of electrons, has to be the same number of electrons lost as electrons gained. In the first half reaction, I lost 1. In the second half reaction, it gained 2. We have to make them the same by distributing to make them equal. So in the first half reaction, if chlorine here needs to gain 2, we've got to go back and double that first half reaction. In other words, we have to distribute a 2 through that first half reaction so that I change the number of electrons lost to match the number of electrons gained down below. Leo must equal Gur. Electrons lost equal electrons gained. So adding them back together. And just as before, when we would simplify, very common, we did this with Hess's law, when we add equations back together and you simplify things that canceled. Think of this arrow as opposite sides of an equal sign. Guaranteed, the number of electrons lost better equal the electrons gained, and they're going to simplify and cancel. And if that doesn't happen, something went wrong, and you just back up and try again. What I'm going to do is add those equations back together, simplifying what I can. Along the way, I'm going to be able to distribute a 2 through that first half reaction. So on the left of my arrow, I have 2 times 1 sodium. I have 2 sodium atoms, no charge, plus, okay, so that's the first half. We're not distributing anything in our second half. The electrons canceled. The only thing left is a chlorine molecule, Cl2. On the right-hand side, distributing a 2 through the sodium ion, 2 units of Na+, and 2 units of a Cl-. Electrons then canceled. The last thing that we always do, just because it's smart business, you double check, just eyeball, does it indeed balance? 2 sodiums, 2 chlorines, but here's the more important part. Are they electrically the same charge on both sides? The left-hand side, sodium was a 0, chlorine was a 0, the net charge was 0. Over on the right-hand side, 2 positive ones with 2 negative ones do indeed balance to 0. What we've just done, a very beginning simple model of a half reaction method. We took an equation that I'm confident you could have just eyeballed and just counted to double those, but we started that way on purpose so that we could use an easy one to begin with. We split them into 2 half reactions and balanced them based on Leo equal Gur. We combine them back together and just simplify what we can. And the last thing we want to double check, not only are the number of atoms the same, but are they electrically balanced as well? The charge on the left equals the charge on the right. That was our first process of an 8-step process in balancing reactions. Let's take a peek at something a little bigger, something that perhaps you couldn't just eyeball and start counting. I noticed in the note pack, again, I have -1s on the sulfite and sulfate, so I wrote myself a note to say, let's remember to fix the charge from what was typed in the note pack. So I've done that on this overhead slide. Sulfite is SO3 -2. A hydrogen ion is placed in here along with the permanganate ion, and that's a -1. On the product side, we have sulfate, which is a -2, water, and a manganese +2. What we're being asked to do is just decide, what do I do to break those into 2 half reactions? What do we see going together in terms of changing charge? And honestly, I don't really have to start by assigning oxidation numbers to each and every element. What I'm noticing is some common elements from the left to the right. If I'm going to create half reactions, I better place the same elements on 2 halves of the arrow, or it wouldn't make sense to balance. Wouldn't make sense to put sulfite with a manganese and try to balance. They're different elements. So when I begin to think about half reactions, I'm going to hook together like elements on the same side. Here's sulfite forming sulfate as my first half reaction. The manganese in manganese peroxide going to manganese plus 2. The like elements here are the Mn. I'm going to hook together in the second half reaction the permanganate ion, polyatomic ion called permanganate, going to the manganese plus 2 ion. Here's the second half reaction method. One of them will be a Leo, the other will be a Gur. What I'm noticing, however, is there's a hydrogen ion and there's a water molecule, and I didn't write about them in the two-half reaction. We're going to learn very soon when we flip the page that those are tools to help me balance. Never include them in the initial half reaction. That H positive, the acid ion, it's just a proton in there. A hydrogen ion is used to balance H's in a half reaction. That a water molecule is a tool that we're going to use to balance oxygens in a half reaction. So if I'm looking at the first half reaction, all I'm doing in this initial step is recognizing how to break a complex reaction that I really would have difficult time trying to eyeball back and forth to balance, just breaking it apart into two halves, creating a half reaction. The steps that we use now to balance these half reactions is that 8-step process we should become familiar with. The reason I just selected this example is to make a note. Hey, note to self, when I'm writing half reactions, hook together elements that aren't H's or O's, that hydrogens and waters are now just considered tools to help me balance. It makes sense because you know the title of our chapter? It's called Aqueous Reactions. Water plays a role in every equation. Aqueous reactions are water reactions. Water's a tool to help us balance. In water molecules, we have hydrogen ions for acidic solutions. We have hydroxide ions for basic solutions. Those are simply tools that we'll see to help us balance. So let's take a look at those rules. What does it mean to balance a reaction using the half reaction method? Keeping in mind that Leo has to equal Gur, we know that the electrons produced must be those required. So all I'm looking here is a little way of saying, as I begin balancing my equation, Leo has to equal Gur. When we break apart the equation, just as I did with that simple one, I was stressing back here, electrons lost has to be gained. And if it wasn't true in the half reaction, we had to make it true by distributing a coefficient. Here's the procedure, and we're going to see that there's two different types of solution, aqueous solutions that occur in acids and aqueous solutions that occur in bases. Let's tackle, I think, the easier of the two first, tackling the steps for acidic solutions. At an example where finally we'll follow all 8 steps. BJ, once again, step number 1, just decide when I'm dividing things into two half reactions, what will I start placing together? Help me write a first half reaction. That's exactly right. In other words, those elements other than oxygens and hydrogens, I better account for them in the same half reaction. It would be impossible to balance an iron and a manganese in different halves. So in a first half reaction, we have permanganate, which is the name of MnO4 negative, forming its ion of Mn plus 2. Taylor, what would the second half reaction look like for this particular equation? Perfect. To the first half reaction, McKenna, we need to balance the permanganate's oxygen. What would I do to balance that? And I think you said H2O, although that trailed off. That's part I didn't hear. Perfect. I balance the oxygens by placing the water on the right-hand side. Step 1, broke it in half. Step 2, the MNs and the FEs all set. Step 3, we've got the oxygen balance by placing waters. Brett, read for us step number 4. Thank you. Notice, by the way, I skipped the second one. I should have made a comment there. There were no oxygens or hydrogens, so I kind of went right by that. Casey, in the first half reaction, we added water to the right-hand side. We got to now back the bus up. Help me balance those hydrogens. Perfect. And I like how you remembered to tell me that the hydrogens were indeed positive. We balanced the hydrogen from the water with the protons. Protons carry a positive charge. Excellent. Rule 5, John says what again?
Valence charge usually negative.
All right, so now we've got to decide what the charge is so far on both sides. Troy, when I look at the first half reaction, on the left side only, what is the net charge so far? With 8 positives and 1 negative? Yeah, good work. +7. Good. Emily, let's look at the right-hand side of that first half reaction. What is the net charge so far?
+2.
Perfect. Aaron, between the left and the right, simple question, which one is the more positive side? Perfect, yep. To the more positive side, that's the place where the electrons will go. So the important thing to remember is we don't make them both become 0, we just make them become the same charge. So to the more positive side, Marissa, how many electrons should I place?
5.
Excellent. 8 electrons to create neutrals. So now, instead of +7, we have it down to +2s. 5. That's what we said. Thank you for catching that, everyone. That's what it says. Perfect. 5 electrons, 8 hydrogens per manganese makes the manganese +2 and water. Now we're both down to +2s. All right. Let's do the same because finally we have something to do for the second half reaction. Courtney, what is the net charge so far on the left side for our iron half reaction? Perfect. And Alex over here? Perfect. BJ, to the more positive side, how many electrons should I place?
1.
On which side?
The right.
Perfect. And now both have become a +2. Nate, read for us back to the top there. What does rule number 6 say?
Multiply equations to make electrons equal.
So Leo has to equal Gur. Taylor, if the first one is gaining 5 and the second one is losing 1, what would I do to distribute to make electrons gained equal electrons lost? Beautiful. We have to distribute a 5 through the second half reaction so that 5 electrons gained will indeed equal or match the 5 lost. Alrighty. Oh, hey, Claire, the first half reaction, I should have said, we might as well just jot it down. It's gaining electrons as a reactant. We put them on the left-hand side. Does that sound like a Leo or a Gur? It is indeed. Gaining electrons is a reduction half reaction. On the second half reaction, Nicole, what would we label the iron to iron +3? It is indeed an oxidation half reaction. Perfect. All right. So we have indeed multiplied equations to make the electrons equal. That was step 6. Nate, back to the reading part. Read for us step 7. Okie doke. So just carrying that arrow right down, everything to the left goes down to the left, everything on the right will be placed here, and if the electrons don't cancel, it's back to the drawing board because that's the whole goal, is to get the electrons to go through. So carrying down everything we have so far, we have 5 negative electrons and 8 positive protons and a permanganate, MnO4, -1. That's the first half reaction. Let's add that together to the second half reaction, and we'll distribute the 5 at the same time. So we have 5 irons that are a +2 charge. Same strategy over on the right side, the product side. We have an Mn+2, and we have some waters, 4 of them. we have to distribute the 5 when we add the second half. So now I have 5 irons with a +3 and indeed 5 electrons. We notice the electrons can be simplified. McKenna, do you see anything else that can be simplified as a double check? Me either. This indeed is simplified as far as we can go. And Brett, one more rule to read, number 8.
Check that charges and elements are balanced.
All right, it's just good business, double check. On the left side, let's count the total charge. Casey, help me add so far on the left side what the net charge ends up being, with 8 positive protons, 1 permanganate, and 5 irons at a +2. 8 positives, 1 negative, and we have a 10. There we go. John, let's do the same thing over here. What do we end up with? I think we got it. Yeah, 2 and 5 units of a +3. 5 times 3 is 15. So that looks good. The charges are matching. That's a double check. And we should just be sure that we have the same number of atoms. Pause here. In this redox reaction, we are going to balance a half reaction in a basic solution. This is probably problem 20.17. For the half reaction in a basic solution, the example gives us OH negative hydroxide forming molecular oxygen O2. The series of rules that we're working to memorize ask us to first divide the reaction into 2 halves. That's already been done for us. This is a half reaction. Step number 2 says balance everybody who is not an O or an H. Well, in this example, all we have are oxygens and hydrogens, so we're all set with Rule 2. Rule 3 tells us to balance the oxygens by adding water. We see on the left side of the equation that we have 1 oxygen, and on the right side we have 2 oxygens. So my first sequence of balancing this will be to add to the left side 1 water. When I add 1 water, I've now balanced the oxygens. Step number 4, let's balance the hydrogens next. And so onto the right side of our equation, I have 1, 2, 3 total H's on the left, so I'll add 3 protons or hydrogen ions to the right. We have the O's balanced at 2 apiece. We have the H's balanced at 3 apiece. We're now ready to balance the charge. When I look at the charge on the left-hand side, we're at a -1. The charge so far on the right-hand side is at a +3. To the more positive side, I'm going to add 4 electrons so that now the charge on both sides is the same at -1 overall. To the more positive charge, I add electrons to equalize the charge. Now, if this were an acidic solution, we know that we would be done, but this is basic, which means we have to turn the number of protons on the right-hand side that we added and neutralize those by adding the base ion to create neutral water. So since I have 3 protons on the right-hand side, to both sides I am going to create 3 hydroxides, so that overall what will happen, these 3 protons and 3 hydroxides form 3 water molecules. And now that's simplified over here. So let's kind of consider the overall simplified equation. We have a total of 1 water on the left with 3 waters on the right. I can eliminate 1 on the left, leaving me a remainder of 2 over here. And I can combine the total number of hydroxides on the left side. And let's just write down what we have. We have 4 units of OH negative, the base ion, forming molecular oxygen O2, and we have 2 waters remaining and a total of 4 electrons. When you check your work, make sure that it's balanced by mass and by charge. We have 4 oxygens on the left 2 and 2 makes 4 on the right. There's 4 H's on the left. We have 4 H's on the right. The overall charge on the left is at a -4, and the overall charge on the right is also at a -4. We have balanced our redox reaction in a basic solution by adding hydroxides in the same quantity as the remaining protons after we've balanced the half reaction. And then decide if they're Leo or Gur. Are they oxidation or reduction? So keep in mind, this isn't a complete reaction. It was one of the first things we did was practicing separating the two. This is 1/2 of a complete reaction. So just a note to self, these are already broken in half. So the first few steps we read out loud together a moment ago have already been done. If I see tin carrying a +2, and now I'm pointing at tin with a +4, it's a half reaction. One of the rules says, break it into half. Number 1, okay, done. It's already broken in half. Rule 2 says, balance everything that's not an H or an O. Done. There's 1 tin on each side. Rule number 3 says, balance the oxygens with water. Okay, there are none. Rule number 4 says, add hydrogen ions to balance the H's. Okay, there are none. Finally, we're to a rule that says balance the charge with electrons. So everything was balanced except the charge. When we balance charge, we add electrons. Electrons are negative. They do not have to be the same charge, or they don't have to add up to be 0. They just have to be the same charge on both sides. To balance this half reaction, it was as easy as adding 2 electrons to the right-hand side. Now I have a net +2 on both sides. When I'm asked if this is an oxidation or a reduction half reaction, the loss of electrons shows that it is an oxidation half reaction. That equation was that easy. Adding 2 electrons to the right side brings both down to a +2 charge overall. The loss of 2 electrons created an oxidation half reaction. Let's show a letter B. Same problem, but we have a little bit more involved. Titanium dioxide produces titanium +2. So this is a half reaction. Rule number 1 in balancing, break them into 2 halves. That's already done. This is not a complete. It's already broken in half. So we would add it back to something else. Rule 1, break it in half. All done. Rule 2, balance everything that's not an H or an O. Well, the titaniums are balanced, so that's good. Rule 3, balance oxygens with water. If I have 2 oxygens on the left and no oxygens on the right, I'm going to balance this by adding 2 neutral waters. Balance the oxygens with water. Now I have the same number of O's on the left as the right. Rule number, next one, I think it's 4. Rule 1, break it in half. Rule 2, balance everything not an H or an O. Rule 3, Rule 3 we did with the O's. Rule 4 says balance the hydrogens. Now I have 4 hydrogens on the right. I got to come back to the left. What we do are add protons. Protons are called hydrogen ions. Since I have 4 hydrogens, I better add 4 hydrogen ions to the left. Hydrogen ions carry a +1 charge. 4 H positives plus TiO2 made Ti +2 and 2 waters. Now we consider charge. On the right-hand side, so far, we have a net +2 charge. Ti +2 is making this a +2. Over on this side, 4 hydrogen ions make this side a total of +4. I don't have to make them both become 0, but I have to make them become equal. Take the more positive side and add electrons to it. The more positive side is the left side in this example. To make them both become the same number, I have to add 2 electrons to the left-hand side. The balanced half reaction would show 2 electrons plus 4 protons plus a titanium dioxide forming titanium +2 and 2 waters. When I add electrons to the left, this is a reduction half reaction. Gaining electrons is called GR. 4 hydrogen ions and 2 electrons brought this from a +4 down to a +2, and now they're the same electrically balanced charge. Step number 1 of our rule says break it into 2 half reactions. That was done for us, so all done. Rule 2, balance everything that's not an H or an O, and that looks good as well. Chlorines are indeed the same number. Rule 3 says tackle the oxygen by adding water. And what I saw, we all placed 3 water molecules on the right side of our equation to balance the O's. Then we back the bus up and take care of the hydrogens, and we do so by adding hydrogen ions. If there's 6 hydrogens on the right, I come back over here and I add 6 hydrogen ions to the left. 6 positive protons plus the chlorate now yield chloride and water. We have it balanced every which way but electrically. When we balance by charge, we use electrons. Remember that electrons are always added to the more positive side. The combined charge on the reactant side, I have 6 positive protons with a -1. So far, this is at a +5. The charge so far on the product side is a -1. We said, think of a number line. If I'm starting at +5, move all the way down to a -1, I'm going to have to move 6 units down on the number line. We added 6 electrons, changing this to the left now to become a -1 charge. The half reaction, if I were to just clean up my answer and write it out, the half reaction would look like 6 positive protons plus 6 negative electrons plus the chlorate yields chloride and 3 waters. We added the electrons to the left, making this a GR half reaction, a reduction. Gaining electrons, reduction. Loss of electrons, oxidation. Let's take a look at our example. Knowing that it's a basic solution, we're going to balance following the 8 steps of acids and adding 1 more to neutralize those protons. We double-checked every element but the H's and O were balanced, so sulfurs are looking good, no need to repair. But I do notice the oxygens. 3 on the left, 4 on the right. So I saw us add 1 water molecule to repair the number of oxygens. Now that placed 2 hydrogens on the left, so I saw you add 2 positive protons to balance the hydrogens on the right. Then we consider charges. So far, the net charge on the left side is a -2. And so far, the net charge on the product side, 1 unit of a -2 with 2 units of +1, that's a 0 charge overall. To the more positive side, we add the electrons to make them become the same charge overall. And we agreed to add 2 electrons to the product side. That makes it become a LEO, an oxidation half reaction. Again, if this were an acid solution, we'd be done, but there's an additional step because it says, oh, it's a basic solution. So we find the number of positive hydrogens we added. We have to neutralize those with the base ion. And what I do to one side, I do to the other. To neutralize those 2 positive protons, we agreed to add 2 hydroxides to both sides. What happens, the hydrogens and hydroxides indeed neutralize to create 2 water molecules. Let's kind of just clean up what we've got written so far. I have a water, a sulfite, and 2 OH negatives on the left. I have a sulfate. H's and OH's combine to make 2 waters. And I have 2 electrons on the right-hand side. I notice one other thing I can do to simplify my half reaction. If I have 1 water on the left, I can take 1 water out of both sides and leave me with a net remainder of 1 water. So my final answer to this half reaction, we have sulfite with 2 hydroxides forming sulfate, 1 water, and 2 electrons. A balanced half reaction for a basic solution.
Let's talk about oxidizing agents and reducing agents in the next series of questions. The oxidizing agent is that reactant that has been reduced, and the reducing agent is the reactant that has been oxidized. For instance, in number 1, solid nickel combines with gaseous chlorine to form a salt, nickel 2 chloride. Nickel, in its natural state, is a 0. Chlorine, in its natural state, is a 0. On the product side, they hooked by charge. Nickel went from a 0 to a +2. It is being oxidized. Therefore, it is the reducing agent. Chlorine was a 0, went to a -1. It is being reduced. Therefore, it is the oxidizing agent. Remember, agents are always the reactants coming from the left side of the arrow. Never pick a product to call it an agent. Let's take a peek here. This looks like a single replacement pattern. Iron 2 nitrate with solid aluminum forms iron and aluminum nitrate. I can clearly see the nitrates are the spectators. Iron started with a +2 charge, formed the element to a 0. Iron went from a +2 to a 0. It is being reduced. Therefore, it is the oxidizing agent. Remember to write the complete formula for the entire reactant. Iron 2 nitrate serves as the oxidizing agent. Iron was reduced from +2 to 0. Now look at aluminum. Aluminum with a 0 went to a +3. It is being oxidized, therefore it's the reducing agent. Elemental aluminum is the reducing agent. Number 3 also looks like a single replacement pattern, so I can tell that chloride is the spectator. Magnesium in its elemental form is 0. When it hooked to create the salt magnesium chloride, it went to a +2 charge. Lead started in the compound as a charged +2 and formed the elemental form of lead with an oxidation state of 0. Magnesium changing from a 0 to a +2 is being oxidized. Therefore, it's the reducing agent. Elemental magnesium is a reducing agent. Lead with a +2 charge going down to 0 is being reduced. Therefore, lead chloride is the oxidizing agent. And one more. Solid nickel assigned a 0. Elemental nickel is a 0. Over here, hooked by charge is a +2 charge. Since nickel is going from 0 to a +2, it is being oxidized. Therefore, we know nickel to be the reducing agent. Hydrogen and oxygen, well, hydrogen's always a +1, oxygen's a -2. This looks to make nitrogen a +5. Over here, it's gone to a +4. If oxygen is a -2, there's 2 of them there, that makes nitrogen a +4. Nitrogen going from +5 to +4 is being reduced. Therefore, we have the oxidizing agent, HNO3. Clearly, making it simple, once I labeled the first reactant, nickel, as the reducing agent, the only other choice for the nitric acid was to be the oxidizing agent. Nitrogen moved from +5 to +4, reduction, therefore we call it the oxidizing agent. Let's continue on. Balancing. We'll work out some simple redox reactions by the half reaction method. These are always a little complex, so I'm going to turn to a pencil. In my first half reaction, we have the permanganate ion, MnO4 negative, forming Mn plus 2. In my second half reaction, we'll hook the methanol, CH3OH, to HCO2H, and I notice we're in acidic solution. Step number 1, divide them into two half reactions. Step 2, balance everything that's not an H or an O. 1 Mn, good. 1 carbon, check. Now we move to balance the oxygens by adding water. In the first half reaction, I will add 4 units of water to get me 4 O's. In the second half reaction, there's 2 O's on the right, but a single O, so I'll add 1 more water to give me a total of 2 oxygens. 2 O's, 2 O's. We'll move to the hydrogen ions, adding protons in the acidic solution. In the first half reaction, there's 8 units of hydrogen, so 8 positive protons. On this side, there's 1, 2, 3, 4, 5, 6 H's. On this side, there's 2 H's. That leaves me to add 4 more protons to the product side. 2 plus 4 is 6. 2 plus 4 more is 6. Now let's balance by charge. In the first half reaction, the net charge is plus 7. In the second half of the first reaction, the net charge is a plus 2. To the more positive side, I will add 5 electrons. Adding 5 negative charges brings both sides down to a positive 2. The second half reaction, 0 is the net charge on the left side, and over on the right side we have a plus 4. To the more positive side, we'll add 4 negative electrons, bringing it down to 0 to match the left. We'll distribute through to the first half reaction. I'll distribute a 4, making the total of 20 electrons, and distribute a 5 through the second half reaction. I'll distribute and add back together at the same time. 4 times 5 is 20 electrons, plus 4 times 8 is 32 protons, plus 4 units of permanganate polyatomic ion, plus distributing a 5 waters, and 5 CH3OH, a molecule called methanol. Let's go to the right side. Up top to the first one, 4 Mn plus 2's, plus 4 times 4 is 16 waters, plus 5 HCO2H, and 5 times 4 is 20 electrons, and 5 times 4, 20 protons. I don't know why I reversed that, sorry. 5 units of the molecule, 20 electrons, 20 hydrogens. That looks correct. Now what can we simplify? Of course the electrons should cancel. How about the protons? 32 on the left, 20 on the right. Let's get rid of all 20 from the right-hand side, giving me a remainder of 12 protons. How about the waters? There's 5 on the left. Let's get rid of all of those, giving me a remainder of 11 on the right. Please rewrite a clean answer just to help me grade faster. 12 protons plus 4 permanganates plus 5 methanols there you go, makes 4 manganese plus 2 ions, 11 waters, 5 organic acids, and that's it. 12H plus 4 MnO4 negatives plus 5 CH3OH. Forms 4 Mn plus 2s, 11 waters, and 5 HCO2H. Here's the second problem, still in an acidic solution. Dividing into two half reactions, As2O3 forms H3AsO4. Keep together the like elements. The nitrate ion goes to the molecular dinitrogen trioxide. We split into two halves. We then have to remember to balance everything that's not an H or an O first, so that's going to make me double the product side on the first half reaction to balance the As, arsenic, and it's going to make me double the reactant in the second half reaction to get the nitrogens to balance. Let's count the O's. 2 times 4 is 8 oxygens, so I'll add 5 waters. 2 times 3 is 6 oxygens, so I'll add 3 waters. Let's balance the H's. 5 times 2 is 10. 2 times 3 is 6. We need 4 more. Let's go to the second half. 3 times 2 is 6. None here, so we'll add 6 protons. Let's balance by charge. This side ends up to be neutral. It's 0. The product side is a plus 4. To the more positive side, we'll add 4 electrons, bringing it down to 0 to match the left. Let's move to the second half reaction. 6 positive protons with 2 units of a -1 give me a net plus 4. Over here is a 0. To the more positive side, we'll add 4 electrons to bring it down to 0 to match the right-hand side. Notice the number of electrons lost does equal the electrons gained, so we do not need to distribute a coefficient as we did in the previous example. We add them back together and simplify. I can see the 4 electrons will simply cancel, so I'll leave them off. On the left I have 5 waters, diarsenic trioxide, 6 protons, and 2 nitrates, forming 2 arsenic acid, H3AsO4, 4 protons, molecular dinitrogen trioxide, and 3 waters. What can we simplify? Well, I notice there's 5 waters on the right, on the left, 3 on the right, so those can be eliminated, giving me a net of 2. 6 protons on the left, 4 on the right. We can eliminate these 4, leaving me a net of 2. So just to clean it up, making a little bit easier to grade, 2 waters, I can just 2 H2Os plus As2O3 plus 2 protons plus 2 nitrates yields to make 2 H3AsO4 plus N2O3. We have one more, and that's in a basic solution. Hydrogen peroxide going to oxygen, dichlorine heptoxide going to the chlorite polyatomic ion. Let's concentrate our attention on the first of the two reactions, H2O2, making molecular oxygen. The O's are balanced, so I'll add 2 positive protons to get the H's. And while I'm here, I'll add the 2 negative electrons to make it electrically balanced. So he's set. Let's go here. Dichlorine, start by doubling the product to get the chlorines to balance. Now we'll move to the oxygens. 7 on the left, 2 times 2 is 4, so I need 3 more waters. 3 O's plus 4 is 7, so that matches. Let's count H's. 3 times 2 is 6 H's. Let's electrically balance. The left side is at a plus 6. The right side, 2 units of a minus 1 is a minus 2. Think of the number line moving from a negative 2 all the way to a positive 6. That's actually 8 units apart on the number line. To the more positive side, I have to add 8 electrons to bring both sides down to a negative 2 charge. The first half reaction, we have to distribute a 4, and we'll add them back together at the same time. 4 times 2 gives me 8 electrons to match the 8 that were gained in the reduction half reaction. We'll distribute and add at the same time. 4 units of peroxide plus 8 electrons plus 6 positive protons plus the molecule dichlorine heptoxide. Onto the product side. 4 times 1, we have 4 molecular oxygens. 4 times 2 is 8 protons. 4 times 2 is 8 electrons. Down below, 2 chlorite polyatomic ions and 3 waters. What can we simplify? Number of protons. 6 on the left can simply cancel, leaving me a remainder of 2 on the right. Electrons always cancel, or we've messed up. That's it so far. If this were an acid solution, we'd be done. But it's not. It's basic, so there's one additional step. I look to find the number of protons. So the very last thing I do is neutralize the protons by adding hydroxides to both sides. So I have to add 2 groups of the polyatomic ion from the base, hydroxide, to both sides, keeping it balanced. 2 hydroxides. Notice now 2 H's and 2 OH's. Well, that's the same as 2 waters. Let's clean it up and write our final answer. The molecule dichlorine heptoxide, gone, plus 4 hydrogen peroxide molecules, plus 2 base ions, 2 hydroxides, forms 4 molecular oxygens, plus, now notice here's some water and water over here yet. Let's combine the total number, 2 plus 3. There's a total of 5 waters. And a ClO2 negative, 2 units of ClO2 negative, the chlorite polyatomic ion. And there is our balanced equation in a basic solution.